Welcome to Learn Data. It's great to have you in this channel. I'm Nilesh, and in this video, we'll talk about semi-supervised learning. We'll look at how it is different from supervised and unsupervised learning, what are the assumptions, and look at two intuition behind self-training and label propagation. The label spreading is similar to label propagation, except in the way in which the matrix, distance matrix, is formed. So we won't be discussing that in much detail, but we'll do talk about the self-training and label propagation. These are two references that this discussion relies heavily on. For self-training, this is the first paper, and the label propagation is the second paper. So the differences between these three is that in supervised learning, as we have seen up until now in all the scikit-learn videos, that the data set is labeled. So each row has a associated label Y, and that's what we have here. So we have two classes A and B shown by the orange and green colors, and those are labeled, so we know what each data point is, and we train the model on this completely 100% labeled data. On the flip side, if we look at unsupervised, which is on the right hand side here, we haven't talked about unsupervised in this series yet, but in unsupervised learning there are no labels. So as you can see here, there are question marks because we do not know the labels. So the methods used to identify groups in unsupervised learning method is by finding clusters. So the orange could be one cluster, then this could be another cluster, and then once you have the clusters, you can label them as belonging to cluster A and cluster B. Semi-supervised learning methods, on the other hand, have a combination of both unsupervised and supervised. So you have a data set in which only a small fraction of the data set is labeled. It could be maybe 2%, 1%, or 5% of the data is labeled. Rest of the data is unlabeled. So what you're trying to do here is use that labeled 1% or 2% small subset of data as a seed to label the entire data set that is unlabeled. And the way that works is that if you have a seed, then a seed data point, that is a data point that is labeled, then the data points in the proximity of that particular data point, there's a high chance that it belongs to the same class as the seed data point. So what you do in the first iteration, you sample some of those, then based on the values for probability, you assign them to class which is nearest to that seed, nearest to the nearest seed, and you iterate these through until finally the entire data set is labeled, and then you train on the final labeled data set to get new labels. So that's how the semi-supervised learning method works. And the reason why this is important is because in many cases it's not possible to label entire data set, and so uh, semi-supervised learning becomes a very important tool to know if you come across a data set that is mostly unlabeled. The main three assumptions that are for this semi-supervised learning approach is that if there are points that are closer together, then they are likely to have the same label. The second is if a data points within a same cluster would have the same labels, and the data lie on approximately the same manifold of much lower dimension than what than the dimension of the input space. Before we get into the methods of semi-supervised methods, I just wanted to share this plot where we have the percent of unlabeled data on x-axis. So 10 meaning that most of the data is labeled, and 90 meaning most of the data is not labeled. So 90% of the data is not labeled. And on the y-axis, we just have the accuracy score that compares the predicted labels by semi-supervised method with the original labels. And as we can see, with most of the data being labeled, the accuracy is much higher. However, even if we have just 10% of the data labeled, still we get a reasonably good accuracy on the predicted labels using the semi-supervised method. And this is on the iris set. These numbers could vary based on the type of data you have or type of the structure of the data. If the data is clustered into densely populated zones and these zones are separated by substantial distances, then it would the method would have a easier job in classifying and labeling those unlabeled data points. But if they are sort of mixed, then maybe the accuracy won't be as high as we see here in the iris dataset. The first one is the self-training. Now, this is from the paper by Yaroski, this first one. So let's imagine if we are working with a couple of documents, and from those documents, we we need to classify which classes each of those documents belong to. So what we do is we pick a polysemous word. But what I mean by that, that word could have different meanings in a sentence. So when put in a sentence, the sentence would have some sense as to what that word should be classified as. So if the word crane, for example, CRANE, uh, it could be the machinery or it could be the bird crane. But when you put it in context of when you put it in a sentence, for the crane is flying, then the sense that we get from that sentence is that that's probably crane with a class bird. And if we say the manufacturing of crane, then we get a sense that okay, that would be the machinery crane that we are talking about there. So similarly to that, here I've chosen a word apple. So it could be a fruit apple or it could be a machinery apple. And here we have the data points associated with those. Now what we can do is from the document we can identify, let's say, this one word apple, and we pull these sentences together, and then either manually or write a code to label few seed points. So this could be, according to the paper, it could be 2 to 15%. And here I've labeled the top 3 as the fruit apple and the second 3 in blue as the machinery apple, and then you have these rest as unlabeled sentences. And this is now the set of data points that we are trying to find to which class each of these belong. Do they belong to the fruit or the machinery? And so we start with these seed data points that we have class A and class B, B for machinery and A for fruit. And with these data points, then we compute the probability distributions and calculate the log likelihood ratios. And based on that, we can assign the neighboring data points to the classes. So we sample from here and then we find that these belong to class A, and then neighbors of these belong to class B. So those are the data points we now found. What the next step is, we consider them as seeds for the next iteration. So we are increasing the population of seed data points. And so while doing that, if there are data points, uh, data points in the same discourse, what I mean that is, let's say if we have a document in which we know that there are data points that are specifically referring to the word fruit, apple, then we would classify the instances of the sentences containing apples in that document as belonging to the same class A. And so that's what this dark line shows, like bridging by considering these to be in the same class as A. And we iterate over the steps until now, and then finally we have all the data points covered. Um, and so now we have clearly identified that points above belong to class A, points below belong to class B. And there could be some misclassifications, and the algorithm has various ways to address those issues. But then once you have these labeled, what you can do next is use those as labels to use those as your labeled data set, and then if new unlabeled data point come in, then you can train on this and try to predict the labels for the unlabeled data set. So that's the 1 sense per collocation method in self-training. Now switching gears here, we'll now talk about label propagation. So imagine we have these 3 data points, and if I say that this particular data point belongs to class A, uh, uh, intuitively we'll think that this point, because it is closer to this data point, it would belong to the same class as this one. Whereas this point on the right hand side is much farther away, and so chances that it belongs to the same class may not be high. So in label propagation, it uses graph theory. So in graph theory, uh, a very basic intuitive uh, understanding of that is each of these data points is connected by a line that is called an edge, and each of the data point is called as a node or a vertex. And this line can have a weight associated with it. So a weight of 0.02 indicates that the proximity of those 2 data points is not much, so they are farther apart. Whereas if the weight is higher, then it means that those data points are much closer together, as shown here. So using this approach, what one can do is try to walk through each of these data points and find out the weights for each of those and see which are closer, which are farther, and based on that we can calculate the probability values and find to which class they belong. So let's say if we have a set on the left hand side here, we have 4 green data points, and the point in the center is the one which is unlabeled, to which we need to find the label. So if you think intuitively, you can you'll right away think that it probably belongs to class that is the green color, because all the surrounding connections to that data point are green in color. Whereas on the right hand side, if you look at this point, again it is in center, it's the same structure, but then the points on the right hand side here, 2 of them are orange. Now it becomes a little difficult to know whether this center data point belongs to class C, or does class green or class orange. And this is where what we can do is find out this is where we can use the weights between each of these data points and try to estimate the probability values, and based on that classify this point either as green or orange. And that's exactly what is done. So the first step is to calculate the weight matrix, which is shown by this relation here, wij which is equal to exponential of minus this Euclidean distance matrix divided by sigma square. So sigma is the parameter that controls the weight that is here, and this is just a difference between the two values of xi and xj. Then using this weight matrix, which is symmetric matrix, you can calculate the transition matrix, which is shown here, which is essentially the weight matrix that is normalized, um, right, as shown here. So the algorithm goes like this. We first calculate this value t into y. So y is the y are the labels, and here the labels, and they are not actual labels. The y is the matrix that has the probability value. So what you do is the seed points, you know that those are correctly labeled. To set the value of value for those points in this matrix to 1 and all others to 0. Whereas if there are data points such as these for which you do not know what if to what class they would belong to, then for this one would be 1 1, this would be 1 1, this would be could be set to zero point 0.5, or if they are more than one, so uh, they could be set at different values of probability, and I'll show an example of that. So you calculate the value of ty, and then you row normalize y, then again reset the values for the seeds, so set them back to 1 and repeat this iteration, and finally you'll get a matrix y that would have a segregated values for probability. So the higher values for the points that are closer and close to 0 values, or low values for points that are away from the, and from that you can calculate what the class of the data point is. This will become much clearer as we look at the example now. Let's say we have these data points that are shown here, these 9 data points. The points in the blue are the ones that are unlabeled, and the points colored ones, that is orange, green, and the red, those are labeled data points. And those are three different classes we are going to look at. And this is in this case we just have two features, feature 1 and feature 2. And so the y that we were talking about in the previous slide, so this y, we can set the value to the initial class probabilities as shown here. So for the orange, this would be the column 1, green column 2, red column 3, and the seed point orange is this one. The others class probabilities would be 0 because we know that it is the orange. And then the second one, green, we have the second column set to 1, the other two are 0. Similarly for red, we have 1 here and the other two are 0. For the remaining data points, for which we do not know the class, we set the probabilities equal, so 0.3, 0.33 for all of them. So each row adds up to 1. So 0.33 plus 0.33, 0.36, 0.66, and then 0.66 plus 0.34 would be 1, and so on for the other ones. Now, as we iterate through the label propagation, after first step itself, we see that the probabilities change substantially. So in this first three rows in first column, we see that there's a shift. The 0.3 values are now climbed up. For this one has gone up to 1. Similarly, this set is changing, and this set has also is changing. And after 50 steps, we see that there's a clear difference in the values. So here these have reached 0.66, 0.64, and 1. This is close to 1, and this is also close to 1, signifying that these data points belong to the class orange, these belong to class green, and these data points belong to class red. So that was how the label propagation works. Now in label spreading, it works in the same way, except that the way the weight matrix is computed is different. And we'll look at the implementation of these in the following video. So the code snippet is as shown here. We have this library, semi underscore supervised and importing label propagation. And we have the train, we have the X values for the features, and then we have the Y unlabeled data, which is shown here in the yellow. And I've added the label data just so we know what to expect if the values are correct or not. So if you run this code, you get Y predicted values, and those should be the same as the Y labeled values that we have here. So that was it for this video. I hope in this video you got an intuition about what is semi-supervised learning, how it differs from supervised and unsupervised, and what are the two main methods that are implemented in Scikit-learn to label the unlabeled data using seed data points in a data set. In the next video, we'll look at the implementation. Until then, please like, share, and subscribe. Thank you.